already.
It's not going to be cold anywhere.
So yeah, we could have to.
All right, let's do this addition reaction.
Arguments, I agree.
Oh, by the way, just take a quick look at this. Again, can't be put together enough. Starting with that material on the left. There's four potential, if you're adding H nucleophile, these again are the four possible scenarios. This carbon has no hydrogens, this carbon has fewer hydrogens, so if the H goes here, that's called a Coulomb competition. If the H goes here, it's anti-Coulomb competition. So here the H goes with this carbon, nucleophile with this carbon, that's more Coulomb competition. Same here, same place. Okay. But in this case, the two groups added are pointing in the same direction, either both up or both down. So that's syn addition. In this case, one's pointing down, the other's pointing up, so that's anti-addition. Okay. Then you could figure out how to get the hydrogen here, the nucleophile here, that's anti-McCollum competition. So again, that's the last bottom two here. The nucleophiles on the end carbon. And the hydrogens here, that's anti-McCollum orientation. And in this case, the two groups are added pointing in the same direction, in this case opposite. So that's syn addition. Here, one pointing south, the other pointing south, so that's anti-addition. So again, those are the four possibilities, but you'll never get all four. You'll get either one or two of those at a time. You can add OH and OH across a carbon-carbon double bond, and it can be added anti or syn. If you start with carbon-carbon double bond, and the first step you add a peroxy carboxylic acid, which is still right like this. More concisely this. And,
Can you move it down,
oh,
please?
I'm sorry. It's getting too late. So carboxylic acid is like this. If R is H, it's formic acid. If R is CH3, it's acetic acid. If R is CH2, CH3, it's propanoic acid. Anyway, that's a normal stable carboxylic acid. If you add another oxygen, then you have a peroxycarboxylic acid. And these are they like to give off an oxygen. So if you take a peroxycarboxylic acid, you're going to get this. This is the insertion reaction I talked about before. But it's not really discussed a whole lot in this book, in this chapter. Later chapter you will see it. So they're interested in addition reactions to form a diol. So they're going to do a second step. They're going to add an acid, H+. They're using water and sulfuric acid. So if you see H3O+, what that usually means is they added water and sulfuric acid. But anyway, so you need to do it in two steps. You can't mix all the ingredients together. But if you do step number one, you get this. And if you add step number two, these ingredients, then you get this. And they point in opposite directions. Okay? Because you're going to protonate this in step one. After you step one, rather, this gets protonated when you add the acid. You have an oxonium ion. Remember before we had a bromonium ion? We had bromine here across this bridge, and we also had mercury across this bridge. So now the next step, water, H2O, can come in from behind. It always comes in, and you're going to get the same product. It's going to attack this carbon, and this perfect goes here. So in the second step, which is well understood, water attacks this, and this bond breaks, and electrons go there. And you get this, and then minus H plus, into the final product. The first step involves, I think, 9 arrows to go from here to here. In the second step, strictly speaking, would be 1, 2, 3 arrows. So we're not going to worry about this mechanism, just way too many steps. But just nice to kind of see how it happens, especially the first step. How does a peroxycarboxylic acid form what's called an epoxide? So that's shown on page 431. And it also actually shows everything, more or less, on 431. So here's an alkene. It's a cyclic alkene. It's cyclopentene. And here's your peroxycarboxylic acid. This R can be just about anything. But anyway, so you got 4 arrows here, all these zipping around, these electrons zipping around. And basically you insert this oxygen in between the bonds. This is the transition state, where these are the bonds breaking and forming. And then you finally get this, you get an epoxide. So we'll come back to this reaction later on. This is an end in and of itself, making epoxide. So you're going to see how to make an epoxide next semester. Anyway, epoxides are not stable under acidic conditions. So the second step now, if you add an acid to the epoxide form in the first step, H plus is fine. So you protonate this. This is going to leave. Let's see, it's a bad leaving group. It's going to leave us a negative charge. So you protonate this. Now H2O can attack this. This flips up here. You get this. Now I usually just put minus H plus. Water pulls this off. But minus H plus gives you your final product. But because attack can only occur on one side, you don't have a free carbocation. You only get one of 2 possible orientations, and you get the anti-orientation. Okay. This is nice. You don't need to worry about who gets what. Is it getting OH or both carbons? So the main thing is which direction in space they point. So if you want anti-orientation with the OH groups, use the peroxycarboxylic acid in the first step, and then water and an acid in the second step. And you get what is called a diol. It's an alcohol. You got 2 OH groups, so they refer to it as a diol. Diols are very high in boiling point materials because they hydrogen themselves very, very well. So, and they tend to be gooey stuff. So, this is ethylene glycol. Has a high boiling point. This is the active ingredient in antifreeze. It tastes kind of sweet when you drink it. Also, you hear about dogs. Somebody will pour antifreeze on the ground, and a dog will smell it and lick it, and they'll die because it forms oxalic acid in your body, and that's very toxic. So, it tastes sweet. It's a poison, but it has a high boiling point. It's a nice thick gooey liquid that can be used as an antifreeze. If you add one more carbon to it, then you can drink it, and it's safe. And it's propylene glycol, and that's used as a thickener in salad dressings. You put salad dressing nice and gooey and thick. It's propylene glycol. Your body doesn't care. It's not going to ice creams and things. Anytime you need a thickening agent, that's what you use. One carbon can make a big difference. Okay. Anyway, the peroxycarboxylic acid is used. Could be anyone, but there's a popular one that's used that makes this. If this acid is too strong, it's going to destroy the epoxide. So you want to make sure your peroxycarboxylic acid isn't too strong. So they have one they like. It's called metachloral peroxybenzoic acid. It's a mouthful. With benzene, this is a carboxylic acid. With benzene and an extra oxygen, it's a peroxycarboxylic acid. This is a chloral group in position in the meta position, which we'll talk about next semester. So this is called metachloral peroxybenzoic acid, and it's abbreviated MCPDA. But any R group here will work. Okay. peroxyacetic acid, that's a little bit too strong. That will destroy the epoxide. So epoxides are sensitive to stronger acids. So if you want to stop at the epoxide stage, they'll use this. You'll see this next semester. Anyway, you can see these bridge intermediates, and if you form these bridge intermediates, the nucleophile that attacks always comes in from the underside, and you always get an anti-addition. Okay, so if you started with this, okay, and you added a peroxycarboxylic acid, you might see RCO3H, you might see beta-peroxy peroxybenzoic acid, you might see that. Same, you know, it doesn't matter. Step 2, sometimes you'll see this, sometimes you'll see this, it's pretty much the same thing. Sometimes you'll see H2SO4 in water. Anyway, so the final product then would be 2 OH groups attached, and they point in opposite directions. Okay, now suppose you want to point in these same directions. Suppose you want syn addition. You can do this. The mechanism is not very well understood, but these are the reasons you use. You want syn addition. And potassium permanganate, usually in a basic medium like citric acid, and usually kind of cold. You might not see cold because, so let's just leave it out. This reaction can get carried away, and you might get other side reactions, so that's why you got to keep it kind of cold. And sometimes we use dilute potassium permanganate, or, this is not and, this is or, osmonium tetroxide, and plus some other reagents, other stuff. I don't remember what they are. There's so many other stuff you can use now. Using sodium sulfite or sodium bisulfite might be other stuff. Plus some of these other communities. Anyway, both of these give you the same product. So both give you syn hydroxylation. The OHs are both pointing up or both pointing down. This method is cheap, but you get a lot of side reactions. So if you're starting material that's very cheap, you gotta use this, and you get the product, but some other side reactions. This is extremely toxic, extremely expensive to work with, but if your starting material is very valuable, you want to use this because you don't have side reactions. You get high yields of this. So there's 2 ways you get this. And both of them kind of, you form a complex in both cases, very, very similar. And they kind of show you the mechanism. In both cases, the carbon-carbon double bond forms a complex with either the magnesium and 4 oxygens. That's MnO4, or the osmonium tetroxide. And you get a lot of arrow pushing and waving, and you end up getting an intermediate, which then reacts in the second step into your product. So it's kind of messy, but it's probably nice to take a look at it, one look at it. Probably the mechanism is not understood very well. The second step. Sometimes the second step always gives them a hard time. But anyway, so here is you get these, this, all this happens. And then when you add sodium hydroxide in a series of sequence of steps, mysterious, and happens that you get the final product. So how it happens, I don't know. Desert manganese, it's cheap, but it's strong oxidizing agent. You tend to get further oxidation of this, so you gotta be careful. Lots of times we'll keep this nice and cold, so it doesn't happen. All right, so that's manganate. Obviously, when you were with mechanism, with osmotic tetroxide, same kind of thing. You get kind of a cyclic intermediate, and then by a mysterious sequence of events, either sodium sulfite or sodium bisulfite, this turns into this in fairly high yields. And they've just come up with a new system, a new way of doing this, which I'm not that familiar with. You can add, besides, instead of adding this and this and this, you can add this and this, or this and this. So you have a bunch of different possibilities. The key is, if we see osmotic tetroxide with anything else, either this, or this, or this, or this, just give me this. Because there's so many things you can add with the osmotic tetroxide. It's just ridiculous to try to remember all the possibilities. But if you see osmotic tetroxide, you know that you're going to turn carbon no bond into carbon plus 2 carbonyl agents. Okay. You know that's going to happen. So that is the way to add OHs. Okay. So we get 3 ways. This is one way. We get syn addition. Here's the other way. You get syn addition. And then the first method, you get anti-addition. Let's see. Let's show you nicer. Cyclopentene, add a peroxycarboxylic acid, you get an epoxide, then add water and acid, you get one up, one down. Okay, that's enough of these initial reactions, right? Okay, one more reaction. This is the easy one. This is just a snip with some scissors. You can snip a carbon double bond and turn it into a carbon oxygen by adding ozone in the first step, and then dimethyl sulfide in the second step. How it happens, that's what I'm going to tell you. Okay, these oxidation reactions involving potassium permanganate, ozone, they're hard to pinpoint. Let me see if they give you the attempt. Yeah, they do. So I'll give you a tip. But anyway, let's just take anything you want to take. Just natural candy or something like that. Let's take this. First step, add ozone. Second step, add, it's called dimethyl sulfoxide. It's 2 methyl groups attached to a sulfur. So dimethyl sulfide, sorry. Dimethyl sulfoxide would have an option, which is dimethyl sulfide. Dimethyl sulfide. Anyway, get your scissors, snip this piece into 2. Or I should say more correctly, just break that bond. And get 2 products. Okay, so see if I can waste a little bit here. Anybody have a rubber band, a small rubber band they can sacrifice, a big fat? I hate one too. here's I have a double bond in the middle, right? Okay, in the middle. So here's my molecule. And so I break it in the middle, and I get two pieces. Okay, so that's what we're doing here. But you don't always get two pieces. Suppose I have a ring compound. This is a ring compound. And I have a double bond somewhere in the ring. Okay, and I break it. I'm going to get one product. So don't be fooled. Don't think that you always get two products. What you do is you snip the carbon double bond. If you have a straight chain molecule that's not a ring compound, then you will get two products. But when you give me the product, you have something like this. Let's get carried away here. These reactions, lots of times, are not synthetically useful because you're taking a complicated molecule and breaking it into smaller pieces. Usually chemists want to take small, simple molecules and make more complicated ones. But this is good for structural analysis. Try to figure out what tech do you have. Bubble ozone into your complex molecule, and a bunch of pieces break off, and you can study the small pieces and kind of work backwards and figure out what your starting material was. So the first case, I would ask you for two products. The second case, I'm just asking you for a single product. So take your imaginary scissors, snip that carbon-carbon bond, and replace it with a carbon option. So if you want to, you could do something like this, I guess. And if you want to open it up, you can. You know, it's not so it's a little tricky sometimes. Notice I still have 6 carbons, right? 1, 2, 3, 4, 5, 6 in the ring. I still have 1, 2, 3, 4, 5, 6. Just that basically take your scissors or your eraser, erase this, and put an option here and an option here. So if it's a ring, you only get one compound. Now, again, this is not that synthetically useful, so in this next test, besides giving you instruments or reagents and asking you for a product, there might be a couple in which I say, what is the structure of the starting material? Some chemists determine structure, so starting material. You have some unknown compounds, they add ozone to it, and EMS, and they get, I don't know, let's get to it. They get 3 products. You give you a possible structure. If I just start with a single compound now, just have one compound, can you tell me what that compound would have to be? That's what chemists would do to his work backwards. A complicated molecule, bubble ozone, followed by dimethyl sulfide, and then analyze it. It's easy to study small pieces, analyze the small pieces, and then work backwards. So it's like having a broken glass, shattered glass, and you have to take all those pieces and put them back together to reform the original shape of the glass. So those are your pieces, and you have to reform the original structure.
if this is the only product, then you had a ring. You're gonna get one product, you know, your strawberry was a ring. And you just swing these two guys together and connect them, but you got more than one product, so you probably don't have a ring. So the answer to this one is how you figure it out. Just line everybody up. Everywhere you see carbon oxygen double bond, was at one time a carbon-carbon double bonds. So these guys were one time connected, and these guys were one time connected. So that would be the structure of the starting material. If you took this unknown compound, bubble ozone, got those three pieces, then you would be able to guess what the structure was. So be able to do, you know, rather relatively simple ones. Not that this is simple. This is what chemists do. Because again, this is not synthetically useful. You don't usually want to make small pieces. You want to make larger, complicated molecules. But chemists are always finding new compounds in nature, for instance, from plants and coral reefs, and they don't know what it is. So they break off small pieces like this, study the pieces, and work backwards and come up with the original structure. All right. And how does it happen? My glasses have never. Anyway, how does this ozone thing work? What's the first step, the second step? Well, as usual, it's like the first step they know pretty well. Second step, they don't know, I guess. They don't take it. But on page 435, at least they show you the first step in a suggested mechanism. So there's the ozone, there's your double bond, and again, you get a lot of arrow pushing here. 1, 2, 3, 4, 5, 6, 7, 8, get to that, okay? So the first step, the ozone reaction, you give this ozonide, and then you add dimethyl sulfide, and in some mysterious way, this turns into this. You know what's happening. You get oxygen, I don't know what you get. Oxygen, you might probably get oxygen gas. Okay, so anyway, that's just for your own interest, that's the mechanism, so to speak. Okay, now at the end of the chapter, there's a wheel of misfortune, so to speak. It shows you all the fun things, 444, that you have learned how to do in this chapter, 444. Now, if I did like 100 reactions, I guess they have it down to 10. And most of these are addition reactions. They're all addition reactions except this one. What we just talked about, this is a cleavage reaction. When you snip this, you see, this is a ring that they snipped. So that's why you only have one product. Okay? And then I talked about insertion reactions. Let's see, where is it? This one, if you just add this, you would insert an oxygen here and you get an epoxide. But in this chapter, they chose not to stop at that stage. Then in the second step, you add an acid, you get the diol. But it is first an insertion reaction with the peroxycarboxylic acid, followed by a addition reaction. But all the rest of these are just addition. You know, skip that one. Number 10 really is the only one that doesn't end up being an addition reaction. So 1 through 9 end up being addition reactions. And then 10 is a cleavage reaction. And they give you some hints to hydro, you know, if it's Markovnikov or anti-Markovnikov addition, can I tell you? They tell you in some cases if it's syn or anti. They should tell you like bromination is anti. For some reason they tell you that. Hydrogen anti. All right, so anyway, there is your
to get a bit kind of messy, I guess. Because now it's just hopping on. But at this stage to me, chapter 7, you learn substitution. Chapter 8, you learn elimination. And chapter 9, multiplication. Somewhere you have heard this. These are the three classes of compound reactions in 438 that you have learned. This is chapter 7. And X, this X was a leaving group, so X was either a halogen or hydroxide. Okay, so so far the substitution reactions you've learned, the leaving group X was either halogen or a OH. If it was an OH, you had to add an acid first to get it to leave, because OH minus is badly leaving. Again, in this elimination reaction, X was also either a halogen or OH. Because you get a dehydrogenation or dehydration. So this is the elimination reaction. This is the one you learned in chapter 8. And that was relatively simple because X was either, again, a halogen that was leaving or an OH. And you gotta have a hydrogen too. So if you lose hydrogen in a halogen, it's called dehydrohalogenation. If you lose hydrogen in an OH, they call it dehydration because hydrogen and OH make water. So those two chapters weren't too bad because you can bank on it. And pretty much in chapter 9, it's mostly addition reactions. The only one that's not is the one with Smithus with ozone, you get 2 pieces. But all the other reactions in chapter 9 will be addition reactions. And it's a bit messy because, X and Y can be a bunch of different things. You can have halogens, hydrogen and halogen, hydrogen and OH, hydrogen and cyanide, OH and OH. There's all these different things you can add across the double bond. See if I can list them all here. HCl, HBr, HI will work, HCN, water, alcohol is not really discussed, but you'll see it later. Then we had then we had halogens. Let me just say XX for halogens, bromine, forever. But you can also have a halogen like bromine, let's say, and another halogen like chlorine. Right? Or you can have a halogen like bromine and an OH. Right? Remember those? So you can have same halogen across, but you can have 2 different halogens or a halogen and OH. Then you can also have OH and OH. I think these are the only ones we covered for addition reactions. Anyway, so it's fair enough. All right, so next week we'll decide if you want to have a test. 2 weeks, that will be the, I guess the week before Thanksgiving, right? 2 weeks from today is tomorrow. Or we can have it the week after Thanksgiving, it doesn't really matter. We can finish this chapter. The next 3 chapters, the last exam covers 3 chapters, they're short chapters. I'm going to get you launched. I know you're tired. I'm going to just get you kind of launched on this next chapter. That will be on the final exam. We will cover together now to the final. So scary. But I don't want to overload your circuits. So let me just give you the next chapter deals with compounds containing carbon-carbon triple bonds. So, this is what you've seen before. You know this is an alkane. Has a general form of CN, H2N plus 2. This is an alkene. Has a general form of CN, H2N. And in this next chapter, we're going to call an alkyne. There's a general form of CN, H2N minus 2. Okay, and so everything you learn about naming alkenes, just extrapolate to alkynes. So if you don't have any double bonds, triple bonds, you know this would be pentane. The name is A, and this is an alkane. If you have a double bond, it's an alkene, so it has an E in the end. And that's before the carbon has the double bond, has to be numbered in this case. You want the lowest possible number, so you can call this 2-pentene. Well, if you have a compound that contains a triple bond, it's called an alkyne, so this would be pentyne. And again, you want to number this location of the triple bond for the lowest possible number, so you call this carbon 1, this carbon 2, and so this would be 2-pentyne. So everything you learn about how to name pentenes, just extrapolate that to pentyne, just change the E to a Y, and everything else is the same. So it's not, not a big leap to go there. You know something like this is cyclohexane. You know this is cyclohexene. And of course this will be cyclohexide. And you know you don't need a number, do you? It's in position number 1. You only need numbers when you have more than one group, like this. Now you need numbers, because the bromine can be here or here or here. And I believe you counted up the triple bonds just like before. So this is covering 1, 2. Get to the groups. You count through the triple bond, through the double bond. So this is going to be 3 bromo. Cyclohexane. So I don't need to say where that triple bond is located. It's in position number 1. Triple bonds in rings are not that common. Single bonds, yes. Double bonds, yes. Why do you think? Think of the hybridization of these carbons, this carbon. Why do you think you don't find that many triple bonds in rings? It's got to be a big ring for it to be a triple bond. What's the hybridization of this carbon? It's got how many single bonds? 1, 2 sigma bonds. So the sp. You know, what's the ideal angle of the hybridization of sp? sp3 is 109.5. Hybridization of sp2 is single bonds. If you have a double bond, the angle is 120. But what about if it's an sp hybridized?
Oh, 180.
180. That's linear, right? The bond is 180. It's a straight line. See, so if you have a carbon-carbon triple bond, it wants to be in a straight line, and here you are curving out, forced into a ring. So you don't have that many compounds, ring compounds with triple bonds, unless the ring is big. You know, if you have a big giant circle, then you can kind of flex it a little bit and make it kind of straight. But if it's a small cyclic compound, it's hard to get a triple bond to fit in there. There's too much angle strength. Okay, so you won't find that too often. There are a few freaky cases where you find it, but not that often. Most of the time, alkynes are straight chain molecules. Okay, luckily there's not that many ways to make alkynes, and so they can talk about preparation of alkynes, and there's not that many chemical reactions of alkynes. Guess what? They undergo addition reactions, just like alkenes, except you can usually add 2 moles across the triple bond, right? Because with the carbon-carbon double bond, you have 1 pi bond, you just need 1 bromine molecule.
But if you have a carbon-carbon triple bond, you have two pi bonds. So in most cases, but there are a few notable exceptions, in most cases, you can have, but not all, two moles across the triple bond. So alkynes undergo addition reactions just like alkenes. So this chapter will still be some overlap, and it's not as long as the other chapters. Okay, so 7, 8, and 9 are the killer chapters in organic chemistry 1. We got 7 and 8 out of the way. So we just got a last, oh, here we go. We got 7 out of the way, this last test. So the next test is 8 and 9, is that right? So those are meaty tests. The rest is not too bad. Okay, I think we'll stop unless anything wants to. Probably had enough. Good sport, you survivors again. Thank you for sticking around.